Example 7.3. Describe the behavior of the inductor's current. Does it store or decay current? Calculate and plot the voltage Vx for all times. A. Physically interpret the inductive current for t equal to 0 minus and t equal to infinity. So that means we have two circuits here. So at t equal to 0 minus, we know that the capacitors had enough time to be saturated. That means it's going to act like a short. So what you're seeing here is that note that the switch closes at t equal to 0, so the 100-volt source is not in the circuit. So I really have the 400, the 600, and then I have the 500 milliamp source. So my first circuit looks something like this. So I have, here's the 400, there's the 600, and then the inductor acts like a short. And then you could see here is that I have my source that looks like this. So here is my current of the inductor looking like that. So you can see that that current of the inductor shorts out. So it kills this guy and that guy. So it sees the full source here. So in this case, this is 500 milliamps. And what you're seeing here is that the inductor sees the full 500 milliamp source. So its current is automatically 500 milliamps. So now what happens at t equal to infinity? So at t equal to 0 plus, I'm saying that at t equal to 0 plus, that turns into t equal to infinity. The 500 milliamp source is now gone because it's shorted out. Now I have 100. So what I want to do here is that I want to convert this into a Thevenin circuit. So here's what I'm seeing here. So I have a 100-volt source, and I have this resistor, then I have this resistor, and then right here, you're seeing that I have my current, and this current here is going to be I infinity, which is I short circuit, which is also IL of 0 infinity. I mean, IL of infinity. Now, if I do a source transformation, look what happens. This source transformation, so this is going to be 100 divided by 40, so that's going to be 2.5, and then I have to adjust for my units here. I'm going to have a 250 milliamp current source. Now, note that I have resistors here. So I have one, that's the 400. Then I have the 600 right here. And then I have the other 400 here. And so when I look at this inductor here, that inductor has this current at I equal to infinity. So what you're seeing here is that I now have what? I have a smaller current source, and it divides the current. So it's only seen part of the 250 milliamp. So what you're seeing here is that clearly the initial inductor current has to be greater than the current at infinity, which is I short circuit. So therefore, we have a decaying current through the inductor. So mathematically, we're going to have to check that. Okay, now let's go to where we need to go. So now we want to determine Vx of t using IL of t. So as always here, I'm going to have to remove the inductive load and start our process. So here we go. Let me bring this all the way up here. So here's what I know. So the first thing that we should do in this process is that just to be complete, we've already done this already, but I'm going to just be complete. I want to determine IL of 0 minus. So before this switch, what do we have? So what we're seeing here, so if I look at the circuit, note that there is no 100-volt source here. And we know steady state has occurred. And then the inductor, because it becomes a short, it kills off these two resistors. So what you're seeing here is that we have no 100-volt source in the circuit. The inductor is shorted and kills off resistors. So if I was to draw a picture, it would look something like this. I would have this resistor here, and I have my short right here, and then I have my source right here. So here's my 500 milliamp. Then I have my current of the inductor going in this direction. But we clearly see that these guys are killed off. Maybe I should have written the numbers here, 600, 400. We can clearly see here that because it shorted them out, that this guy is then going to be 500 milliamp or 0.5, that half an amp. So now I've got my first step. Okay, let's go to step 2 now. So now what I got to do here, because this is an inductor, our next step 2 here is that we want to determine the Norton parameters. At t equal to 0 plus. So what do I mean by the Norton parameters? I need I short circuit, the Norton resistance, and then the time constant. So what happens now, if we come back here, note that the switch is thrown that kills off the half an amp current source out, and now it brings in the 100-volt source. So let's go draw this out. So at this point here, we see here is that there is no 500 milliamp source. And the 100-volt source is active. So when I look at my circuit, I'm really looking at a circuit that looks something like this. I have 400, I have another 400. And then I have my inductor. And then here I have my voltage source. So I know that this is 600, this is 400, 400, and then right here is my inductor current that I'm going. Now, when I look over here, this is ultimately the voltage that we're looking for. Okay, so that's my circuit now. So that's the one I gotta pay attention to. So here we go. Let's do it. So the first thing that I need to do here is that I'm going to determine I short circuit. Now that means that the inductor is a short, but note that that inductor is in series with this 400 ohm resistor on the right. So when I redraw the circuit, I'm not going to have a short for the inductor. I'm just going to look at that 400 ohm. So now what I'm going to do here is that here I replace inductor with a short. And so I have an effective circuit that looks something like this. So I have 100-volt source. I have a 400. I have a 600. And then look how I'm drawing this. I have my 400 right here. So here's my 600, 400, 400. And I'm saying that this current right here is I short circuit, which is also the current of that 400 ohm resistor. So now I got to calculate what that current is. So the way I'm going to do that is that I'm going to get the voltage across the 400, and then I'm going to use Ohm's law to get the I short circuit. So I'm going to use VDR to calculate the voltage that's the 600 parallel to the 400, but because they're in parallel, that's also the voltage of the 400. And I'm going to use Ohm's law to get I short circuit. So here we go. So the voltage divider rule then tells me that if I want the voltage across the 600 parallel to the 400, this is the same as the sum of the series resistors divided into the resistor that I want times my voltage of 100 volts. If I calculate this, I get 37.5 volts. And this is the voltage of the 400, since they're in parallel. Now, looking at Ohm's law, I now see that the current of the 400 must be the voltage of the 400 divided by 400. And so when I divide 400 into 37.5 volts, I get 93.8 milliamps, or I can also write this as 0.0938 amps, and this is I short circuit. So now let's go see. I now want to do that important check. So when we interpreted the inductor, we said that IL of 0 was going to be higher than I short circuit. Let's compare them. So I know that I initially was at 500 milliamps versus I short circuit, which we just calculated, is now 93.8 milliamps. So you could see that this guy is greater. So therefore, this tells us here is that the inductive current decays. So that means at least we're moving in the right direction. Okay, now let's go to the next step. We want to determine the Norton resistance and 1 over tau. Again, because we have no dependent sources, I'm going to use method 1 to calculate Rm. So we short out the voltage source. Look at my source here, right? I'm going to short out this voltage source right here, and my inductor is removed. So then my circuit looks something like this. So I'm going to have and there's my shorted source right there. And then you could see here that I'm going to have this guy right here. So this is 400, 600. This is 400, and we want this guy right here. So if I follow my ohm meter, you can see here it's going to go here, and then right here it's going to split. So if I calculate this thing, you could then say that Rn, I'm going to have the 400 in series with 400 parallel to 600. And if you compute that number, you get 640 ohms for Rn. So now if I look at my time constant then reads RTH over L, which will then be 640 ohms divided by 0.1 henries, and that gives me 6,400 hertz for my 1 over tau value. So now I got the two values that I need the most to complete my solution here. So here we go. So now that I have that, I'm now on step 3. And in step 3, I'm going to put into solution form and interpret. So solution form tells me that this is the inductor current, which will be I short circuit plus IL of 0 minus I short circuit e to the minus t over tau. So if I put in my values, I'm going to get 93.8 plus 500 minus 93.8 e to the minus 6400 t. So in the end, you could see that this value reads 93.8 plus 406.2 e to the minus 6400 t milliamps. And this here is my inductor current. So if I look at this, I'm seeing a couple of things here. Here's what we see. First of all, this plus sign tells me that I have a decaying current. And then this quantity right here, this says that it decays by 406.2 milliamps from its initial value. And this guy right here is the final steady state. So when I look at this thing and if I plot this, what am I actually seeing? Well, I'm going to see something like this. So what I see here is that I have my current coming in, and this is IL of 0, and this guy is 500 milliamps. And then what it's going to do here is going to drop by 406.2 milliamps all the way down to 93.8. So if I look here, what you're seeing here is that I'm now going to get my final steady state I short circuit that's 93.8 milliamps. And as it drops, it's going to go something like this. And so now what you're seeing here is that this is a decay of the current by 406.2 milliamps. Decay. Which is exactly, we knew that there was going to be a decay. Now the equations tell us exactly by what that means here. So let's look at this thing just a little bit longer here. So let's go through a series of questions. So the first one I'm going to ask is IL of 0 minus the same as IL of 0 plus? We say it's continuous, but what does this say mathematically? Well, this tells us here that IL of 0 minus, we already calculated that from the circuit, and it's this. And then I'm going to compare this to IL of 0 plus. So this tells me that this is going to be 93.8 plus 406.2 times e to the 0. And you could see here is that this is also 500 milliamps. So the answer is that there is continuity in the inductor here. Now, another thing that we should look at here is that note that is the voltage of the inductor equal to the voltage of the inductor afterwards? We expect that it shouldn't. The voltage can change. Now, here's what we know. We know that the inductor is acting like a short at 0 minus. So that means that VL of 0 minus is 0. So now the question is, we want to compare this to the inductor voltage at 0 plus. So this we're going to have to calculate. So now the calculation shows that it should be L di dt of 0 plus. So if I compute that, here's what I get. So calculating this, what we see here is that VL of 0 plus is going to be what? I have my inductor value, which is 0.1. Then I got to take the derivative of the inductor here. So if I take the derivative, note that the first term is going to give me 0 because I got 93.8. So that's going to give me 0. And then I have plus 406.2. And then I have to take the derivative of this exponential, which brings down minus 6,400. So then I'm going to get times minus 6,400, but this is in milliamps, so I got to put in a minus 3 there. And this will be e to the 0. So if you compute this number, the number that you get here is you get minus 260 volts for VL of 0 plus. So let's compare them here. So I have VL of 0 minus is equal to 0 versus VL at 0 plus, and this guy's equal to minus 206 volts, 260 volts. And you could see here that when I compare these two values, there's a discontinuity that occurs. So the inductor voltage will change instantaneously. So this tells us then that VL of 0 minus is not equal to VL at 0 plus, as expected. Now we got to solve the circuit problem. So what I'm going to do here is that I'm going to go in and I'm going to get the circuit that we drew up earlier. And we go on to our next step, our final step. And here we want to solve the circuit problem for Vx of t, which is of course the same as the 600 of t. So let's go do that. So what is our circuit? So here is our circuit. So all I did is I went in and I copied what we had before. And here it is. So this is our circuit here. We have now calculated IL, and now we want to calculate this Vx. So what I'm going to do here is that I'm going to apply KVL over the right loop. So let's apply KVL around the right loop. So if I do that, note that that Vx is then going to be the voltage across the 400 plus the voltage across the inductor. But what this means here is that using Ohm's law, I know that this has to be, since the 400 and the inductor are in parallel, that has to be 400 times IL, and then I have to take the derivative of the inductive current to do that. And again, IL is 93.8 plus 406.2 e to the minus 6400 t in units of milliamps. So let's go do that. So the first term you could see here, so if I look at that 400 tells me that I'm going to have 400 times the inductive current. So I'm going to get 93.8 plus 406.2 e to the minus 6400 t. Now and remember, these are in milliamps, so I got to write -3. Plus, I now have to take the derivative. Now note, we've taken the derivative already before, but we set t equal to 0, but in this case, I'm not. So I'm going to have 406.2 times the derivative of the exponential brings down minus 6400, and then I get my exponential term right back, like that. And of course, this, because it's milliamps, I got to write -3. So when the dust settles, you're going to see here is that I'm going to collect the two exponential terms. And if you look at all of the numbers, it's going to look something like this here. So you could see that the big difference between, well, there is some difference between the numbers. Maybe I should write them out. So then this guy's going to give me what? I have 400 times 9.83 times 10 to the negative 3. That gives me 37.5 volts. Then I have my second term. So if I look at my second term, look at the exponential term. I have 400 times 406.2 times 10 to the minus 3. And then I have my second term here. Now note that there's a minus sign, so I'm going to carry that minus sign out. So I'm going to get minus 0.1 times 406.2 times 6400 times 10 to the minus 3 e to the minus 6400t. So if I now add all these numbers together, I'm going to get minus 97.5 e to the minus 6400t. So this is my voltage of this guy right here. So now I know what that voltage is. So now I want to interpret this voltage, okay? So to interpret it, I really have to do three things. I'm going to summarize this. I want to plot it and interpret as much as I can. So what do I know about this guy? So the first thing that I know is that I know that Vx of t has three things that we got to look at. So we have 37.5, and then I have a minus sign, and then I have 97.5 e to the minus 6400t milliamps. So let's go through this. This guy right here, this is the final steady state. So that means that it's not milliamps, by the way, it should be in units of volts since this is a voltage. So that means it's going to reach its final steady state of 37.5 volts. Look what the minus sign says here. So if I look at this minus sign right here, this minus signs that there is a storing of current. And then this next piece here, 97.5 tells me by how much does it increase in this case. Well, it increases by 97.5 volts here. So now, here we go. So I know the final steady state. So the first thing I got to do here is that I have to determine, I have to calculate Ix of 0 minus. So if I look at my circuit at t equal to 0, here's what I see. I have a resistor here. I have a resistor here. And then I look at my short here. And then I have my current source, which is the 500 milliamps. So this guy's 500 milliamps. And we know that because of this short here, all of the current goes to the inductor. And since we have already defined this as Vx of t here, you could see that these guys are shorted out. So this immediately tells us that Vx at 0 minus should be 0. Okay. Now, because this is a resistor, we expect this a discontinuity. This is a resistor. We expect a discontinuity. where Vx of 0 minus should not be the same as Vx of 0 plus. They could be the same, but then the circuit is going to actually have to force it to do that. So here I go. So Vx at t equal to 0 plus means that I have to use my thing here. So if I look at my solution, this is going to be 37.5 minus 97.5. And this is e to the 0. And this gives me minus 60 volts for Vx of 0 plus. So right away, what we're seeing here, as we already expect here, Vx of 0 minus is not the same as Vx of 0 plus. So now the only thing that I have left here is that I need to plot Vx of t. So if I look at this guy, it's going to look something like this. So so this is Vx of t. And I'm going to call this t. So here we go. This thing comes in as 0. And that's because the inductors are short. So Vx of 0 minus, I get 0 volt. Now there's a discontinuity of minus 60 volts. So this guy's going to drop all the way down right here. So that this is Vx of 0 plus is equal to minus 60 volts. And now what it's going to do here is that we know that the final steady state goes all the way up to here. And so that means here is that this guy, we know that Vx of infinity, which is its steady state, should then be 37.5 volts. So then that means this guy's going to come up and it's going to reach steady state like that. And if you look at the jump here. The jump from here, this is the voltage jump of minus 60 volts for that resistor.